Thank you for watching Knowledge Academy.
Okay, in this lesson, we will be learning about Jacobian. Before we start a mathematical part of Jacobian, let's take a look what is Jacobian is and how do we actually apply the Jacobian in real life. So let's suppose I have a distorted shape is given. If it's a regular shape is given like this, and if I'm asking you give me the area, you say this area is x and y. You area multiply, you give me the x times y. No problem, issues is solved. But if I have a distorted shape, let's suppose the shape is like this. And in this shape, if I am asking the area or any other shape that the area is being distorted, that will be a little bit challenge for me. How can I measure the area? So what I'm gonna do, I'm gonna be making two axes like this and two lines like this, and rotate this line and rotate this line, or rotate only this line or rotate this line based on my need. And the red color line is going to be look like this, right? And what I'm going to be doing, I basically start changing, rotating my head. Let's suppose you are watching this, and what's happened, you have eyes here, you try to watch this guy. One way is to deal with this like with an angle, or what you can do, you can rotate your eyes or you rotate your head. So this, the red color axis is going to be converting into this new axis, this one, and this area is going to be look like this. These new axes, which is a red color axis, I'm going to call them x and y, and maybe I'm going to call them u and v, or maybe you could call them anything, wx or dj or uv. you know Now there is a relationship between, and that's actually the Jacobian. When you try to mimic the shape from one coordinate system to another coordinate system, or a better way to say is from one axis to another axis, right? That's how Jacobian is being used. So there is a relationship between v and y. There is a relationship between u and x, and there should be something written here. There should be written something here, right? Same thing when I say the area equals to xy. Now the new area equals to u times v, but there should be a scale factor. And this scale factor is actually Jacobian. Correct? Now if I want to be talking about how can we do a little bit more in a better way in a integral format, because we are the integral or calculus student, we're learning things about an integral form. So let's take a look how we can write in a Jacobian in integral form. I'm going to write in the white color, this one. I'm going to be writing like this, r f x y dA. This integral actually gave me the area for this white color region. Okay, just so you know, this region is not exactly same in size as this region. If you want to overlay this region, right, if you want to overlay this region over here, it could be maybe this and this. It maybe could be this and this. Maybe it could be this, that, right? So it's not exactly same. So I'm going to complete my statement. So I'm going to write this area should be equals to, in new integral system, I'm writing r. So I cannot write r anymore. I should be saying s, something else. So I should be saying something else, which is maybe I say s. And the function is pretty much same, but function was in xy format. Now function is another function in u and v format. And I have two axes, both going to be changed with respect to x and y. So x is going to be changed and y is going to be changed. So I have to bring another axis coordinate system. So I'm going to be saying one is G, one is H. So this side is G maybe, and this side maybe H. Both are changing. And then U and V. Really, this guy is nothing, is basically transformation from here to there, here to there. Now this part is done. How about this dA? Usually we write dA equals to dx dy, but I couldn't do it dx and dy because dx and dy changing to du and dv, right? So I'm going to writing here du and dv. But there's another problem. When I multiply x and y, and I get the answer, right? When I multiply u and v, because u is not equals to x, you have some factor here, some factor, I don't know, 1.32, this one is 0.98. I need to multiply these two factor too, so this factor is going to be stuck into the between, and that is a Jacobian. I'm going to write here, and maybe I can change the color and writing here. That factor I'm going to be writing, right, this factor times du dv. This factor is being written in the differential form, is in a little bit different way, and maybe I can write here like this. Yep, all I did, I finding the change of x and y with respect to change of u and v. I can also write this du and v in another form. I can write like this. I can just write in the form of matrix. Okay. I can also solve the integral, so I'm going to multiply this to this, that to that. So I can also write this one like this. Dx du dy over dv minus dy over du dx over dv. And this thing, actually the yellow thing I just wrote here, that is my Jacobian. Yeah. And that's what exactly we need to focus on today's lecture, how these different Jacobian is going to be calculating and determining. So let's take a look few example for Jacobian coordinate system and then go from there. Go. Sketch the image as in the UV plane of the region R. In the XY plane using the following transformation. Now, usually when I say using the following transformation is nothing but it's just a relationship between x and u and y and v. So for example, I have given x equals to 3u plus 2v and y equals to 3v. It means how much is the shape distorted. Usually this guy is given to you. Okay. And the shape is given in x and y. So this is my x, this is my y. It's giving 1, 2, 3, and then 1, 2, 3. So right now we are here, somewhere here, and that is my 0, 0. So I'm gonna make this guy here and this guy here. So it's gonna be touching there. Okay. Now the thing is that we need to take a look. This region and is given in the form of y and x. So this is my 3, 2, 1, 1, 2, 3. The coordinate of this point is 3, 0. The coordinate of this point is 2, 3. This coordinate is 0, 0. That is my r. Remember, it's distorted. I want to rotate my head while I'm looking this. I want to rotate my head while I'm looking this. So what I'm going to do, I need to convert a solution. So first of all, I need to convert from u to v, from x to u, and y to v. So I need to change these two equations in the form of u and v. So v equals to 3, sorry, y over 3. V equals to, from this equation, y divided by 3. And u equals to x minus 2v over 3 from this equation. Equation number 1 and equation number 2 transform into u and v form. Okay. Now I'm going to make a table. This table I'm going to make two columns. The first column is x and y value. The other column is u and v value. Now I'm going to take three values given to me. Number one is 0, 0. The other one is 3, 0. And the third one is 2, 3. I want to substitute these values into different form of x and y. So if I take x, 0, x and y 0, 0, I'm going to substitute here 0, so v becomes 0. So v becomes 0. And from here, I'm going to take this v and substitute here. So v is 0, then x is 0. So 0 minus 0 divided by 3 is going to be 0. That is my u and v value. Same thing if I take x equals to 3. So 3 divided by 3, v equals to 1. V equals to 1. So I'm going to say is 1. Okay. And the other value should be 0. If I substitute that one, 1 minus 1 is 0. Last one is when I take the x equals to 2 and substitute into the equation, I'm going to get in 0 and 1. Okay. Now what I'm going to do, I'm going to be draw the sketch, because that's what you have to do. Sketch the image in S. So the new image, it will be in S form. In the S form. So I can do the same thing. 1, 2. Maybe I can do this time a little bit better. Since my value doesn't go from more than 1, I'm going to say is just 0, 1, 0, 1. So 0, 0 is 0, 0. 1, 3, 0 turned into 1, 0, so it becomes 1, 0 here. The other value is 0, 1 is going to be turning here. So if I connect them, that is my new region. The region I'm just going to highlight in the yellow form. That is my new region by using Jacobian transformation, right? and the name should be something, and this is S. Okay, that's actually the Jacobian. It's kind of a itchy topic for students, but let's do another example. I'm not gonna write in the question, I'm just writing the transformation and shape. So in this problem, the transformation is giving something else. X equals to 1 over 3 4u minus v, and y equals to 1 over 3 u minus v. The shape giving something kind of. I think I'm making a little bit. I'm gonna make like this. The coordinate of this giving 0 to 0, the coordinate of giving 4 to 1, the coordinate of this point giving 6 to 3, the coordinate of this point giving 2 to 2. Okay, all I can do is taking this and do my I want to convert x and y into u and v, so I need the u and v equation in the form of x and y, or vice versa, but I need the equation for u and v, not x and y. X and y is given. This is x and y for me. Okay, so I'm going to be converting them. U equals to x minus y, v equals to x minus 4y. Okay, you can do a little bit more math to just transform. So I convert everything x in the form of u in the form of x, then replace from the v from the second equation, substitute, so everything will be gone from the v, only thing left over is x and y. Same thing for equation number 2. I just a little bit transform in two different ways. So it's gonna come here, it's gonna come here. Anyway, we're gonna be substituting the values into these equations. So this equation, I'm gonna take this table, saying this is my x and y, this is my, sorry, it's gonna be, yeah, u and v. So I have 4 points, 0 0, 4 1, 2 2, and 6 3. When I transform, it's going to be 0 0 pretty much. Here I have 4, so 4 minus 4 is going to be 0, so 3 comma 0, 4 minus 1 is going to be 3, and then the other one v will be 0. 2 2, so I'm going to substitute 2 2, so x should be 0, or sorry, u should be 0, v should be, if I substitute 2, and 2 minus 3 times 12, 2 minus 12, 3 is going to be minus 6. And this one is going to be 3, right? And 6 minus 3 is going to be 3, and the other one will be minus 6. Okay, if I want to transform this and then write into the, or draw into the, look like everything is going into a lot of things in the minus, so I should be drawing this like this way, and that is my u, and that is my v axis. So I'm going to go to 0 0, is going to be 0 0 here, then 3 0 is going to be here, then maybe this guy is 0, minus 6 will be here, and then 3 minus 6 will be here. So that is my 3, 1 2 3, and then 1 2 3 4 5 6. So I can just connect these dots, call them S, and then basically shade them with some color, and that is my new region. All I did, I just rotate my head. I just rotate my head. Okay. Now sometime equation is given in the little bit more in the not in a coordinate form, not the coordinate form, they given in the form of points in the equation form, not in the coordinate form, in the equation form. So what we can do, take a look in the problem. Let R be the region bounded by the lines x minus 2y equal to 0, x minus y 2y equals to minus 4. So these are the two lines, and then x plus, not x plus, x minus, no, x minus 2y is done, x plus y equals to 4, and the last one is x plus y equals to 1, as shown in the figure. And the figure is giving something look like this, this, and is giving 1 2 3 and 1 2 3. The shape is giving something look like this, it's about right before 1 here, so go here. So I'm gonna write like this. It's passing from one point, by the way, this point, and it's gonna go this way. It's passing the point 2 this way, and the other point is gonna be like this. The 4 lines I was talking about, these are the lines. It's gonna be the 4 lines given in the problem is gonna be these lines. Let me write the equation of these lines. X minus 2y equals to 0. Then x minus 2y equals to 4. So minus 4. It's gonna go other way, minus 4. This line equation is x plus y equals to 1, and this equation of this line is x plus y equals to 4. The question is given, evaluate the double integral. Yeah, which integral? Like this. Now you know that we just talk about that. We need to just say x and y relationship from these equation and finding into u and v, and then converting to Jacobian. So what I'm going to do, I'm going to start the solution. So I'm going to assume something here. I'm going to assume x minus 2y equals to v, right? X equals to maybe I can say minus 2y. Let's say u equals to x plus y, and v equals to x minus 2y. How do I came up with this? See, this is a common. So if you see this is common, like this is common and this is common. So one should be this, and then this guy and this guy common. So the second one should be this. So I came to relationship with making them. Sometimes the relationship is given, sometimes we have to make our own relationship. So what I'm going to do, I'm going to just add the two equations. So x minus 2y equals to v, and x plus y equals to u. I'm going to subtract them. Okay, so x is going to be cancelling out. This is going to be minus 3y equals to v minus u. My goal is to find the u and v equation in the form of x and y. Okay, so here I can find y equals to minus 1 over 3 u minus v. Okay, I can take, sorry, I just already get inside, so there is no minus here. All I did, I just rephrase this equation. That is my v value, u and v value in the form of y. Then I'm going to substitute this into the first equation. X equals to u minus y, and x equals to u minus 1 over 3 u minus v. And I'm going to just take the LCM, so it's going to be 3u minus u plus v divided by 3. If I further simplify, x equals to 2u plus v divided by 3. And that is my second equation. Okay. Now I know when I do my Jacobian, right? My Jacobian equals to 3u times v times Jacobian du dv, right? So I'm going to be just go to the next slide and talk about that. So really, by Jacobian theorem, I'm going to be writing my integral like this, the given integral 3xy dA. That should be converted into like this. 3 is going to be u, and x and y is converted into the form of u and v. So I'm going to substitute the value of x and y, the one I'm getting from here. These 2u minus 2uv. So it's going to be look like this. The x is replaced by the value I just show you. Y value is also replaced by the value I just show you. So it's going to be look like this. 1 over 3 2u plus v. 1 over 3 u minus v. Now this x and y converted, this is u and v, so they're going to be multiply the u and v as well. And when the u and v multiply, all the other things should be coming with Jacobian, and that's the thing we just wrote here, we call Jacobian, and that's should be written like this. And now dA basically replaced by dx dy. So I multiply the two, u and v, and this is my leftover factor. This is called Jacobian, and now the last operator should be dv du. Okay, this is called Jacobian. So my goal is to find the Jacobian. Okay, and I'm going to just write here, this is my Jacobian. Now I need to find the Jacobian, which is this. I can write this into the vector form. So dx in the matrix form. And multiply this minus this. Okay, that's what we learned. But what I can do, I have two equations are given in the previous slides, like x in the form of, so x equals to x equals to 1 over 3 2u minus v. We just discovered that one, and y equals to 1 over 3 u minus v. We already discussed that where this equation came from. This is the one we explore right here. Okay, so I'm just writing those equations. So what I can do, I can find du or dx from here. If I do du or dx, it's going to be equal to du or dx equals to 1 over 3, I believe. Du dx over du is going to be 2 over 3. So 1 over 3 is coming out, and then when you take the derivative of du with respect to u, is going to be just 2. And then v becomes 0 because v considered as a constant. We taking partial derivative, so 2 over 3 is left over. Then dx over v, the answer is 1 over 3. When I take the derivative with respect to v, this whole thing 1 over 3 comes out, and this du becomes 0, and minus is going to come out, and we can write over here. Now I have dy over du. So dy over du is going to be equal to 1 over 3, and dy over dv is equals to minus 1 over 3. Yeah. What I can do now, I can just apply this determinant. I can solve the determinant because it's in a numerical form, easy to solve it. So I'm going to say is 2 over 3 times minus 1 over 2 is going to be minus 2 over 9. Then minus from the formula of determinant, and then 1 over 3 times 1 over 3 is going to be 1 over 9. If I solve, it's going to be look like minus 1 over 3. So I'm going to go back to the third slide and solve this one. So I'm going to take this equation and substitute all the values I have. All I do just take this red color Jacobian and substitute this value over here, and rid of this guy, and then rest of them will be easy to solve, just like double integral. The only difference here is I do not have my x and y replaced by v and u. So what I'm going to do, I'm going to just write in here 3x y dar plus 2 s 3 1 over 3 we just need to solve it since it's given in the form of x and y. And now I'm going to be just rid of this guy, right? And then substitute what was the answer, minus 1 over 3 minus 3 dv du. If I simplify this, I'm going to go here and take a look on the v and u from the diagram. So v value is going from if I substitute the value of here, v value is going from minus 4 to 0, right? And u value is going from 1 to 4. If I substitute, if you take these values from u and this guy, this value, this value, this value, you know x and y from here, just like we used to do it. We're writing this table, and I have x and y values, so it's going to be, you're taking from here 0.5 and 1, and substituting the value of u, y, and find the value of u and v, x and y from u and v. So all I can do, I can go there and typing my values. It's going to be this, the new values 1 4, and then multiply this, try to simplify. It's going to be 1 over 9 2u square minus uv minus v square I just did one step, a little bit drag to simplify it, to save our time. You can multiply, it's going to become out something look like this. Okay, and now we just treat the integral for this is going to be 0. I'm going to take 1 over 9 outside and 1 4 2 u square v minus, I'm taking the integral with respect to v, and so u is considered as a constant. 3. I take the second integral, but before than that I need to substitute the limit. So it's going to be 0, so it's going to be 8u square plus 8u minus is going to be 3 times 4 times 4 16 and 64 divided by 3. I'm going to take the second integral, 1 over 9, then 84 u cube over 3 plus 8 divided by 2 is going to be 4 u square minus 64 divided by 3 u, and limit is 4 and 1. If I substitute the limit, I'm going to get this. And that is my answer. Okay. Take a look, one last problem real quick. I have shape is given, integral is given, I need to convert into that. That is r 4 x square plus y square dA. Here x is given and y is given in the form of 1 over 2 u plus v, and v is given u minus 1 over 2 u minus v. So 1 over 2 u plus v, and y is given 1 over 2 u minus v. The shape is also screwed and distorted. It's look like this. It's gonna be something look like this. This is a given. Everything I written right now in a yellow form, a yellow text is gonna be given. 1 0 and 0 1. This one is minus 1 0, and this one is 0 minus 1. Okay, so this is my 0 0, and the region I'm going to be about to shade, I just call them, this whole region is R. This R region. Yeah. Now the thing is, if I'm asking you calculate the area for this region, it will be a little bit challenge. It will be challenge. So what I'm going to do, I'm going to be rotating this guy either this way or this way to make them these lines align with x-axis. So my goal is that moving this line and this line in a much more a systematic or uniform or standard way of axis, so I can calculate the area of this shape, because this shape looks awkward shape. Okay, and that is where the Jacobian play a role to come up this. So I'm going to convert xy, which is already given, x equals to 1 over 2 u plus v, and y equals to 1 over 2 u minus v. I want to calculate, first I want to calculate the Jacobian. My Jacobian is this matrix, right? The matrix of this dx over du dy over dy dy over dv, right? And then dy over dx and dy over dv. So I can just write this one in a more determinant form. You can also write, whenever we do this determinant, we always write in this form. Minus dy over du dx over dv, and then solve it. That's my Jacobian in a pretty much same Jacobian in a form of equation. So I'm going to take the x derivative with respect to u. If I take the respect to u, answer would be half. If I take the y derivative with respect to v, this is one is going to be half, and v with respect to, I think, is minus half. It's going to be minus half. Minus, then I'm going to be taking the derivative of y with respect to u, so it's going to be just half. And just take with respect to x with respect to v, it's going to be just half. If I solve, then minus 1 over 4 minus 1 over 4 is going to be minus half. Minus half. That's an answer. And I'm going to do one direct step, just substituting the values. So r 4 x squared plus y squared dA equal to. Now I'm going to be substituting the limit of u and v. So I'm going to take the value of this 0 and 1. I'm going to writing a chart right here. See, this is my x, y. That is my u and v. So 0, I'm going to say is 1 0, right? 1 0. So my limit, I'm going to go by limit. So x value is this to this. So I'm going to say is 1 0. And this one is going to go to whatever 1 2 3, and the other one will be 0 1, and it's going to be minus 1 0 and 0 minus 1, and then you substitute this value into this equation to finding u and v. Okay, so I'm going to be writing this and doing one direct step. So I finding those values. So I'm going to writing 4, rid of this 1 over, so I'm going to be taking this guy 1 over 2 u plus v and square. Okay, and then plus 1 over 2 u minus v and square, and then a big square, the big bracket, and then I'm going to put the Jacobian minus 1 as 2 from here. I'm going to substitute here, and then dv du, and I need to substitute the value of these limits. So it's going to be minus 1 to 1 and minus 1 to 1 after this transformation from the table. Since I have a limited space, maybe I can write a little bit better. So what I can do, I just write this guy. This guy is 1 over 4. 1 over 4. And then I can also change these bigger parentheses. So I don't need all these. I don't need all of that. Right? I can write maybe square, square. If you apply the a minus b, a plus b square, you're applying this guy, a plus b square and a minus b square. So it's going to be a square plus 2ab plus b square identity, and a square minus 2ab plus b square identity here and here. It's going to be look like this. It's overly simplified. U square plus v square, then d v d u equal to, I'm going to take the integral for the inner side, minus 1 1, then 2 u square plus 1 over 3 d. I don't need this. And I'm going to take the second integral. I did one direct step, 2 u cube over 3 plus u over 3, and then 1 minus 1. Let's substitute the limit here. It's going to be 2, 1 is going to be 1 over 3 plus 1 over 3 minus, and it's going to be minus 1, so it's going to be minus 1 over 3 minus 1 over 3. So here I think plus, it's going to be plus, going to be plus, both are plus and these are the plus. So if I add them, 3 3 3, so it's going to be 8 over 3. It's going to be 4 over 3, and you multiply by 2, so it's going to be 8 over 3, and that is my answer for the new region. Do I have to draw that one? If I'm going to draw this 1 1 minus 1 1 1, is going to be look like this. It's going to go here and there, go here and there. So this is going to be 1 minus 1. It's going to be 1 comma 1. It's going to be 1 minus 1 comma 1, and this is going to be minus 1 1, and that is my new region. In which format? In basically in S form. See, R from S. Okay.
Thank you for watching Knowledge Academy. Please subscribe my channel.